And here we are again with another projectile motion problem. So thinking through this process, we are assuming air resistance is non-existent. This particular problem specifically states that, but even if they do not specifically state that, we are assuming that for now. So gravity, once the ball has been hit, the ball only experiences the acceleration of gravity until it runs into something else. We know this ball will not travel in a straight line. It will have some sort of parabolic motion. The way this is worded, when it says it's barely clearing the wall, we're going to assume the position of this ball to be 21 meters high and 130 meters from home plate. We're told the ball is hit at an angle of 35 degrees to the horizontal. So just drawing my velocity vector, 35 degrees here. It will have a y component and an x component. But in this particular case, we do not know the initial speed. So we do not yet have enough information to find numerical values. We can say that Vx initial is going to be V initial cosine 35 because the x component is adjacent to that angle, but we don't know the value of V initial, but that's okay. We don't want to stress a different setup. We'll still just continue pushing through with what we do know. The y component being opposite the angle will be V initial sine 35. So let's go ahead and set up the table. We know this motion is not straight line motion, so we do need to break our problem into x and y components. We know acceleration is constant because we're ignoring air resistance. So as long as we're accounting for where the ball is just moving under the influence of gravity, we can use these kinematic equations. So I'm going to go ahead and set up that table we've been talking about. And again, we have to do so for x and y individually. And that's just because it's not moving in a straight line. All right, we need to choose an origin. We can choose that origin wherever we want it to be. If we go ahead and just call it at the ground, like I've been doing before. So at the ground, right initially where the ball is hit, that would mean the x initial is 0, but y initial will be positive 1. Because we're assuming the ball is hit at a height of 1 meter above the ground. Finally, we're telling us the ball has been just barely cleared this wall. That wall is 130 meters away, so that would be our final x position. And we're told that it is 21 meters tall. To just barely clear it, we're essentially saying the ball is just barely above 21. So by saying 21, we're okay. This initial velocity, we do not have numerical values for because we don't know the initial. And that's what they're asking us to find, is this initial speed. But I do know that whatever the initial speed is, the x component can be found by the initial speed times the cosine of our angle. The y component can be found by the initial speed times the sine of the angle. Now I'm putting that in because the problem has given me the angle, so I'm going ahead and writing it as specifically as I can in terms of the information given. The final velocity we know is the same for x because this ignoring air resistance. We do not know what it is for y, but we do know the acceleration is downwards at 9.8 meters per second squared. We don't know time. We know it's the same for x and y, but we don't know the value. So in terms of the information given, v final for the y direction we don't know, time we don't know, and this v initial, this initial speed we don't know. Okay. This is where we would often start to panic because we don't have enough information to actually solve for anything yet. But let's not panic. Let's continue moving through the same process as we have before. So for example, in the x direction, we have found that just the middle equation is what ends up being useful. So for the x direction, we can say that that final, let me write it this way first. The final x position is equal to the initial x position plus vx initial t plus 1/2 ax t squared. But again, because there's no acceleration in the x direction specifically, that third term is gone. The origin I've chosen is making the initial position for x 0. We do know this final x position is 130 meters. I'm going to go ahead and put that in. I don't know the value of Vx initial, but I know I can calculate it if I happened to know V initial. V initial meaning the initial speed the ball was hit at. That times the cosine of 35 would give me that Vx initial. And then, of course, I need to know time. How long was this ball traveling from when it was hit to when it got to the wall? So I do have two unknowns. That's fine. It's a little different. Previous problems, we only had one unknown. But again, just keep going. Previous problems, we had to use the y direction for some information. So let's go ahead and explore that for a minute. The top equation, the top kinematic equation, v final in the y direction would be this initial velocity sine 35, the y component of the velocity. Acceleration's 9.8, and then time. So here we actually have three unknowns. We don't know Vy final, we don't know V initial, we don't know time. The middle equation, S final y, would be S initial y plus V initial yt plus 1/2 ay t squared. We do know the positions. So we could say 21 is equal to 1 plus this V initial sine 35 is how I would find the y component if I had it, if I had the initial speed. I do know the acceleration in the y direction is negative 9.8. When I multiply that by 1/2, I get 4.9. So I can write that as minus 4.9 t squared. So this top one had three unknowns. We now have two unknowns. The bottom equation, I would have Vy final as an unknown and V initial as an unknown. So I would still have two unknowns. So regardless of the equations we write out, we have at least two unknowns. Well, you have at some point solved systems of equations, meaning two equations, two unknowns. In the x direction, I know my unknowns are V initial and time. if I can find an equation describing the y direction in those same two unknowns, then I can solve time in one, plug it in the other, because I know time has to be the same for both. V initial, the overall speed, has to be the same for both. So the top equation, this one had 3 unknowns, so I don't even want to bother with that. This middle equation we wrote out has V initial and time. Those are the same as the unknowns I have for the x direction. So this is the one I actually want to use. So what we're going to do is, for the x direction over here, I'm going to solve for time symbolically, well, just in terms of these numbers I know and V initial. I can't find a numerical value at the moment because I do not know V initial. But I know the time is the same. So I'm going to go ahead and bring the 1 over. So I'll have 20 equals V initial sine 35. In place of time, I have 130 over V initial cosine 35 from the x direction. And then I need to put it in for time again, and this one needs to be squared. All right, so 20 is, in this first term, the V initials will cancel. I have sine 35 over cosine 35. Sine over cosine is tangent. And then I still have the 130 there. So this term right here ends up being a number that we can calculate. The last term we can factor through as well. I'm actually going to leave it this way for just a second. And I'll show you why. We can square factor through at any stage. I think I'm just going to minimize the algebra a little bit. So 20, I'm going to bring the 130 tangent 35 to the other side. And then I'm going to divide by negative 4.9. That will leave me with this stuff squared. I'll then take the square root of both sides. I'm going to go ahead and find out what number that gives me on the left side. So 20 minus 130 tangent 35 divided by negative 4.9. Square root of that. So this left side becomes 3.8073. The right side, the square root is going to get rid of our squared. So I'll just have the 130 over V initial cosine 35. Bringing V initial up here to the left and dividing the 3.807 to the other side. Times the cosine 35, 41.684. Now I need to revisit the problem to see how many significant significant figures I need. I tend to forget, so I need to go visit again. So this one is 3, 35.0 is 3, the 1 is 3, 130 is technically 2. So I would say V initial is 42 meters per second. If the ball, this baseball, was hit at 42 meters per second at an angle of 35 degrees above the horizontal and a distance of 130 meters from the wall, it's gonna just barely fly over the wall for a home run. All right, this one, of course, this problem is significantly harder than the previous one, mainly because we end up with a system of equations. You do, as long as you can still recognize that we need to split into x and y, we can use the kinematic equations. We want to start writing these values out. So like V initial, even though we didn't know the value of V initial, we wanted to write out the x component and y components in terms of V initial and then sine and cosine of the angle. By doing that, we have them both in terms of V initial, meaning the same overall initial speed. So that makes it just one unknown there when we throw in the angle. Then we start putting things into the equations. When we cannot solve an equation right off the bat, just start setting up other equations. If none of them can be solved right off for a number, then that means we have a system of equations. We want to make sure we have the same two unknowns, and then we can substitute. Throughout this semester, we will have a lot of problems that involve systems of equations. Here, this is, in terms of this first section, this is the main point. We'll have a system of equations, but it will come more often. Okay. I'll do one more example along these lines where we have a system of equations, and then we'll be done with examples. So please ask questions when you have them.